So why do we care about this? Because motion in space can be modeled as a vector. So you can look at changes of at changes in space of position as a kind of vector. So imagine that we have a particle here at time one, and it moves through space, and eventually ends up here at time two, and we want to know the distance or what kind of the change in location, the displacement between here and here, time one and time two. So how do you do that? Well, you set up a coordinate system. You basically lay out a grid mark on your map, and you set up an origin. You say this is the place that I'm starting at, and you draw a pointer to the first spot, and then draw a pointer to the second spot. Okay, now these pointers are arbitrary because my coordinate system is arbitrary. I could call this 0, I could move this around and put it wherever I want to. But if we look really carefully, what we see is that if we take this vector, which I'm calling R1, this pointer to this spot, and add to it the displacement, which is the actual motion of the actual real body from here to here, that's vector addition. That's head to tail addition. So this vector here, R2, is the sum of R1 and delta x, the change in position. So R2 is equal to R1 plus delta x, or we could rewrite this as delta x is equal to R2 minus R1. So this displacement is the change of position, and it measures how far we've gone going from time one to time two. Okay. Now notice this delta x is independent of our coordinate system. If I imagine grabbing this and moving it around, the vectors r1 and r2 will swing around with me, but this vector delta x stays in the same spot. And so this is how we assign a displacement or a change in location to a particle in space. Okay, so Newton's law says we need to specify constant motion. So have we done so just by doing this? No, that's not quite all. All we've said is where is the body at two different times. We've not really said how is it moving. So we have to do one more bit of work to turn this vector of displacement into a vector that actually tells us how the body is moving. And that is to define something called the velocity. So consider the displacement delta x is equal to r2 minus r1. So that's our change in position. We're interested in the rate of change of position. So the rate of change of position is the change in the position, which is a vector, divided by the amount of time it took to go between those two positions. So I'm here on my map on day one, and I'm here on my map on day two, and it took me 24 hours to go from here to here. And so I could take the distance that I've traveled here and divide it by that time, and that will tell me how many miles I've traveled in that 24 hours. That's the rate of change of my position during that time. So quantitatively, that's the position vector r2 minus the position vector r1 divided by time 2 minus time 1. Well, time 2 and time 1, those are just scalars. Those are just numbers. They're not vectors. So I can pull that out and just call that 1 over delta t. And delta x is a vector, so what I have is a scalar times a vector, which means that this quantity, whatever it is another vector, right? If I take and multiply a vector by a number, I get another vector out. I just make the vector longer or shorter by the amount of the scalar. And so here I get a new vector, and that new vector we're going to call the average velocity. So velocity is basically the speed and direction of a of motion for a system. And so this definition should make sense. It's basically how far you've gone and what amount of time. And we could say that's the average speed. I know if I travel 100 miles in 10 minutes, that's a speed. That's 100 miles per 10 minutes. We could convert that to miles per hour or whatever units we want to use. And so this vector captures both the idea of how fast we're going and also what direction we're going, because it is a vector. It's an arrow. It's not just a scalar, just a number. But this is not quite good enough, because Newton 1 asks us to specify the state of motion at a particular time right now. How are we moving when the particle is right here? What direction is it moving, and how fast is it moving? Not how far it moves between two times, but how far it's moving at one given instant of time. And so the way that we do that is by specifying something called the instantaneous velocity. So what I like to use with my students is analogy of a police officer and a radar gun. So you're driving down the interstate and you're moving from your initial location to maybe you're driving from work home. And you know that if you take the distance from work home, say that's 15 miles, and divide it by the time that it took you to get home, let's say it took you a quarter hour to get home, then 15 miles in 15 minutes, that's 60 miles an hour, right? Is that, yeah, that's 15 miles, that's 60 miles that's 1 mile per minute, 60 miles per hour. Yes, sorry, 60 miles per hour. So that would be your average speed for that whole trip. So if you get pulled over and the police officer comes up and asks you, do you know how fast you're going? If you say, well, my average speed was going to be 60 miles an hour until I got pulled over here, he'll say, well, I'm not interested in that. I'm interested in the speed that I clocked you at when you passed me at that one moment of time 2 miles back. And he said, that's the speed that I care about, and that's the speed where you are going much faster than your average speed. And that's what instantaneous velocity is. It's how fast you're moving at the moment when you get caught on the radar gun, not the average between 2 points. So how do we get that? Well, it's really easy. We just take the average and shrink the time that we use to measure the average. So in calculus, we say that we take the limit as we let that time get closer and closer to zero. So as the measurement time for the average gets smaller and smaller and smaller, we get closer and closer and closer to the speed that we are actually going. And that we're going to define as the velocity or the instantaneous velocity. So no one ever really talks about average velocities in physics. When we talk about velocity, we're always talking about the instantaneous velocity or the speed and direction that you're moving at a moment of time. Okay. Now, there are actually 3 different ways of writing this, and they're all useful and they all come up. We could just write v for velocity, and it's a vector quantity, so we put the little arrow over it. We could say dx dt, which is to be read as the rate of change of position as time changes. So the rate of change with respect to time. The other way that we say this is that this is the derivative of position with respect to time. Physicists get tired of writing this notation, and Newton had his own different notation. This notation was actually invented by Leibniz. And Newton invented this notation where he put a little dot over top of the symbol. So this is the position vector, and the dot means how the position is changing with time. So the dot is how the position is changing with time. All 3 of these are equivalent, and again, sometimes we write them one way and sometimes we write them the other, depending on the context in which makes the most sense. So what we're able to do now is really specify motion. So we know now that when we say constant motion, what we're saying is we have a particle at a particular position and that it's moving with a velocity v, and that when that particle is at a new position sometimes later, it's still moving with the exact same velocity v. That velocity doesn't change. So velocity specifies the state of our system, and Newton 1 says that in the absence of external forces, our velocity doesn't change. So the last thing that we needed to talk about, to specify, is what do we mean by change of velocity? How do we measure a change of velocity? So the rate of change of velocity, this works exactly like velocity for position. Velocity was the rate of change of position. Now acceleration is going to be the rate of change of velocity. And it's the change in the velocity over the time change. So velocity 2 minus velocity 1 over the time difference between time 2 and time 1. Again, we see that this top quantity here is a vector minus a vector. That's a special case of vector addition. So this quantity is a vector. And then T2 minus T1, that's 1 over a scalar. This is a scalar. We have a scalar times a vector. We get a new vector out, and we're going to call that the average acceleration. So just like we had an average velocity, if we know what the velocity is at one time and know what the velocity is at another time, we can use this equation to calculate the velocity between the average acceleration between those two times. But once again, we don't care about average acceleration. We want to know what the acceleration is at any given moment. How is the velocity changing at an instant in time? And we do the exact same thing. We define the instantaneous acceleration, which is the limit as our time interval gets smaller and smaller of the change in the velocity vector. We call that the acceleration. And again, now we have four ways of writing this. We can write this as the derivative of the velocity or the change of velocity with respect to time. We can write that as v dot. So the dot here means the first derivative of velocity with respect to time. But the velocity is the derivative of position with respect to time. So velocity, remember, velocity is equal to x dot. So velocity dot is just equal to x double dot. And so again, this is common notation in physics that we have this acceleration is the second time derivative of position. It's how position changes not with time, but with time squared. So you'll notice the units on acceleration are going to be position, which is measured in length, divided by time squared. And that's why we have things like, I guess I should say t squared. That's why we have accelerations being things like 32 feet per second squared. That's the acceleration due to gravity, as an example. So now we can actually really understand what Newton 1 says. Newton 1 says that when there are no external forces, acceleration is zero. So the acceleration is zero means that the velocity won't change, so that no matter what we do no matter when we look at our particle, it may move from one spot to the other, but its velocity, the direction it's moving and how fast it's moving will never change because our acceleration is zero. And that's Newton 1. Okay, so that was a lot, but I told you Newton 1 is a lot more subtle than people give it credit for. There's a lot of information that has to be defined and understood before we can really understand what Newton 1 says.